Hello everybody, today we are going to focus on earthquakes. So we're going to do a quick overview of earthquakes. So please make sure you have this worksheet out, your outline notes, and we are on page 6. We'll start right here with earthquakes, and let's get started. So our objectives here today for earthquakes. We are going to define what an earthquake is and what causes them. We'll list the parts of an earthquake. We'll let you identify 2 ways that earthquakes are measured, and we will quickly talk about the 3 types of seismic waves. And this will be a quick overview, and we'll get into more details in the upcoming days. So, starting off, earthquakes. What is an earthquake? It's any vibrating, shaking, or rapid motion of the Earth's crust. Most occur when stress builds up along a zone of weakness or a break in a rock known as a fault. So if you see this diagram right here, this break in the rock right here, this is called a fault. So a fault is simply a fracture or break in the rock where movement can occur. When the crust shifts, energy is released, and the energy radiates outwards in all directions through vibration. So you'll see that happening right here. Here's our fault running all the way through the earth, deep down inside the earth, and as these move, eventually they'll give way and energy will be released in waves traveling outward in all directions. Let's take a look at that. So if we take a look here, a quick example, you'll see stress being applied to the rock. The rock will bend, but it doesn't bend too much, and eventually it will break. That break is called the fault, and you can see that the earthquake occurs when it shifts quickly. So we apply force, it tries to bend, but eventually it'll break and our earthquake will occur. Similar thing happening right here. There's our focus along our fault line. That's where the earthquake first happens as the rocks shift and the energy went out in all directions. 2 points here that we'll talk about. Focus is the center point where it originates, and the epicenter is right above it on the Earth's surface. Now where this can happen would be a place like this. Here's our transform fault boundary between North America and the Pacific Plate. As one plate moves one direction, the other one slides in a different direction, and they grind past each other, releasing energy, making an earthquake. Alright, back to the notes. Parts of an earthquake. The place underground, as I just showed you, where the break occurs, is called the focus of the earthquakes, and that would be right down here, the origin point deep underground. The epicenter is the name of the location at the Earth's surface, and it's going to be directly above the focus. Essentially, it's the first place that these earthquake waves reach the surface. And we'll see that again in this picture right here. Notice the focus is going to be deep underground, and the epicenter will be right above it. Focus, waves hit here first. This is your epicenter. Next, we want to look at measuring earthquakes. There are 2 main ways we measure an earthquake. Well, first let's take a look at that's called measuring its magnitude, which we use a scale called the Richter scale that you've probably heard about. Here we use instruments called seismographs that are most reliable measures of an earthquake. What they'll do is they will measure the shaking of the ground. And what's interesting is each increase in 1 unit of magnitude measures a 10-fold increase in shaking. In other words, a 5.0 is 10 times greater than a 4.0 for earthquakes. The other way that they're measured is by their intensity, and that would be on something called the Mercalli scale. And this is based on the amount of damage that they see. So here it's based on the reports of people who experienced the earthquake and observed the destruction. The reason why there's 2 different scales is the Richter scale measures the amount of shaking, but the Mercalli scale measures the amount of damage. And it is possible to have a lot of shaking but not much damage. That might happen in a desert or places where there aren't any buildings. Or you could have a lot of damage happen in an area that, from an earthquake, that might not have been as violent a shaking, and that could be in a heavily populated area, or maybe places that were made out of brick. Stone buildings are not very flexible and they tend to have a lot of damage. So there's 2 different ways earthquakes are measured. And here's a quick look at them. On the left side is the Mercalli scale, which is the amount of damage, and the right side would be the Richter scale. So, for example, for a 1 and a 2, for modified Mercalli scale, it would be felt by almost nobody or felt by very few people. The Richter scale, it's not felt, but it's recorded with seismographs, seismic meters. If we look at a measurement of a 4.5 on the Richter scale, which says that some damage may occur, well, the Mercalli scale, which actually talks about the amount of damage, would say it was felt by many people. People ran outside, furniture was moved, Some structures could have had considerable damage as well. So the two different scales that you see here. Now the seismometer or seismograph that I was talking about looks like what you see right here. And basically what it is it's a revolving drum of paper, and it's attached to the ground. As the ground moves, the paper moves with it. But you have a pen that's freely hanging with this weight on it, which will tend to stay still. So as the earthquake occurs, what you'll notice that happens here is everything moves, but the pen pretty much stays still. To you and I, it looks like the pen is zigzagging, but actually if I run this again, the pen's going to kind of stay still where the arrow is, and the ground shakes back and forth. And this is going to create our zigzagging line on a seismograph, or a seismogram, which is this piece of paper here. And we're going to see a couple of waves here, a P wave, an S wave, and an L wave, or a surface wave. The P wave stands for primary wave. That's the first one to arrive. Then the secondary, S for secondary wave. And finally, your surface waves would be the third one. And we're going to look at these a little bit more specifically now. But before we do that, let's take another quick look at a seismogram. You can see that the ground is shaking, but the pen is remaining still. And we can get the zigzagging lines drawn of how much the ground shook. Again, P wave, S wave, and surface wave. Notice the amount of zigzagging that occurs. P waves show the smallest amount of zigzag, where the surface waves have the largest. And real quickly, one more seismograph. This one shows the up and down motion. The last one showed the side to side horizontal, and this is how we would measure the vertical up and down shaking. Alright, so we have our seismographs, which gives us things called P waves, S waves, and L waves. Let's take a look at those. So back to our notes. P waves. P stands for primary. They are the primary waves. They are the first to arrive. These are pressure or push-pull waves. The material expands and contracts, and particles move back and forth in the path of the wave. And these waves will travel through solids, liquids, and gases. And let me show you what a P wave looks like. So if we look right here, a P wave is a compression wave that you see happening with the slinky here. It's being compressed, and the coils are compressing in the same direction that the wave goes. Another way to look at it is kind of like this. They're compressing in the same direction that the wave goes, and one more example would look like this. So you can see we have compression happening here. That's a P wave or a primary wave. Next up is an S wave. S stands for secondary wave. So this one will arrive second. It arrives a little bit later after the P wave. This S as in a shearing wave or a side-to-side wave. Here the material shears out of shape and snaps back. And this travels only through solids, and that's important. That's where we got to the old outer core being a liquid, because S waves do not travel through it. So let's take a look at some S waves. We'll let this run through. There's our P wave. Coming up next is an S wave. An S wave would be as if you snapped down on a rope, and your wave goes up and down, but yet it moves to the right. There's our P wave, and here's our S wave again. So you snap it up and down as the wave moves down the rope, and you'll see it happening here on the road. It kind of moves side to side motion. Back to the slinkies, the S wave kind of looks like this, as if you move a slinky to the side. And our last illustration, the S wave kind of goes like this. Notice it's going up and down or side to side as the wave moves or propagates from left to right. And the final type of seismic wave is a surface wave, sometimes called an L wave. And these travel along the Earth's surface. Now it's called an L wave because that stands for longitudinal. We can't use S for surface because S already stands for secondary. So our surface waves, they travel along the surface. They're the slowest waves, but they're the ones that cause the most damage in large earthquakes. Why? Well, because all the stuff to damage is on the surface, and the surface waves will cause the most damage. Let's take a look at them. We'll run this animation again. P waves, compressions. S waves, side to side. Here they are with the ground going side to side. And here comes our Rayleigh waves, which are surface waves. And what we have is a circular motion happening here, much like an ocean swell. And it causes the ground to go up and down, much like swells you'll see on the ocean. And what happens is, if you look at all these structures, it literally throws them up in the air and then they come crashing back down again. And that's what will cause most of the damage in earthquakes. This is what knocks buildings down. The building actually gets thrown up in the air a little bit and then falls back down to earth and crashes and breaks as it falls back down. Okay, back to the notes to finish up. Earthquakes epicenters. Well, seismologists, those are the scientists who study earthquakes, and they figure out where an earthquake occurred, where the epicenter is, by using the difference in the speeds of the P and S waves from 3 seismic recording stations to locate the epicenter. They use 3 seismic stations, so it's called triangulating it, much like GPS does, and we'll get into that in a little bit more later. But what happens is, they're going to look at the difference here. If we look at this line graph, we'll see that the P wave, here's our distances, in order to go 5,000 kilometers, P wave takes about 8.5 minutes to go that far. To go 5,000 kilometers, the S wave takes about 15 minutes. See that? The S wave goes a lot slower. Scientists will, or seismologists, will actually use the difference in time here to figure out how far away the earthquake was. And once they do that with 3 stations, they'll actually be able to pinpoint exactly where the earthquake occurred. So to find the origin time, what time the earthquake started, a seismologist needs to know the arrival time and the travel time of the P waves. And they can measure the difference between the P wave and the S wave to find out how far away the earthquake was. And if that seems a little bit confusing right now, don't worry about it. We'll get into it a little bit more in the next day or so. Well, real quickly, this is how that works though. Let's go back. What you'll see here is at one location, notice the P wave got there first, and the S wave is a little bit slower. P arrived, then the S arrived. So the P got there first, then the S. These two are 2 minutes apart. But if we go to station B down the bottom here, let me run it back, we're a lot further away. The P wave still gets there first, then the S wave, then the surface wave. However, here they are 4 minutes apart. Since they are 4 minutes apart, that's because they took a lot longer to travel. So by measuring this distance, they can see that this distance was greater. Let me show that to you again one last time. By measuring the time difference, short distance away. Long time difference, long distance away. So that's how scientists will measure earthquakes. So what they're going to do here is they're going to measure the P and the S time difference at 1, 2, 3 stations. They're going to use this on the graph that I just showed you before. So they're measuring up the P and the S. You'll see the different times. One of them was closer. Another one was a little bit further away from the second station. So it's either going to be here and here. Well, when we bring in our third station, we'll see that all 3 of these stations intersect at one spot right here. And that's where the earthquake's epicenter was. And we'll do a lab to show you how this works, so don't worry about it. But real quickly, what you want to see happening here is we have our seismic stations. They get our P and our S waves. We measure the time difference between the P and the S wave. We want to do it for 3 locations. So we have Denver, St. John, and Lima. We get the time differences, 3, 8, and 12 minutes, and a 3-minute gap, an 8-minute gap, and a 12-minute gap will give us certain distances, and we'll figure that out in class. And we plot those distances on a map. We get the distance for Denver, the distance for St. John's, and the distance from Lima, Peru. And all 3 of them will intersect at one spot, and that's the epicenter. So that's how we know where earthquakes occur. And finally, we are going to look at an earthquake shadow zone, and I'll read this to you, and then I'll show it to you real quick, and we'll be done. When major earthquakes occur, both P and S waves are received over most of the Earth. However, the opposite side of the Earth will receive P waves, but no S waves. S waves cannot penetrate the liquid outer core, because we learned earlier today that S waves only travel through solids. There's also a region where neither P waves nor S waves are received, and this is called the shadow zone, where nothing reaches it. Refraction or bending of the waves at the mantle core boundaries cause this ring-shaped region known as the shadow zone. And I'll show you some animations of that. So if we take a look here, we can see P waves and S waves, and notice we're going to get this cone-shaped shadow zone where no waves are hitting at all. It's right here and over here. So the shadow zones are here and here. We'll do one more animation. So real quickly here, you're going to see the P waves in black, sorry, the P waves in dark blue and the S waves in light blue. And if we take a look at this, we'll see that the P waves and S waves both travel through the mantle. The P waves go into the orange outer core, but not the S waves. See how the light blue does not enter it? And as we continue all the way down, we're going to kind of get this gap in here, and this is our shadow zone. So we can see how earthquake waves were used to tell us about the inside of the Earth. A little bit more sophisticated, but you'll see the same thing happening here. S waves do not penetrate here at all. Here's all of the S waves, and you can see they don't go through the center. And there's a little bit of our P wave bendings. These are P waves, but since they bend or refract, we end up creating this shadow zone on the left and shadow zone on the right that I just talked about. So to finish up, you'll kind of see the same illustration here. P waves travel through the outer core. They bounce around. They can travel through all the way out the other side where S waves cannot. So here's a diagram. A little confusing. You don't have to worry about it too much. Just realize that the S waves do not go through this outer core. You can see them stopped right here. All right, that's it. Please go back, rewind, and fill in anything that you need.